Okay, so this next video is going to focus on probability, but it's going to be more simplistic than what you might get from reading most stat textbooks. We're going to focus mainly on statistics as used in research and may not get so much into how a lot of stat classes that teach intro to probability may focus on different games and pretty unique circumstances. So we're going to focus primarily on stats as it relates to how research studies and epidemiological investigations may be done. So probability in the simplest terms. For more information on basic probability, there's a few pages in the online textbook that will relate to some of what we cover here. You may get a little bit more information on unique situations that may result in more interesting takes on probability, but we're going to keep it pretty simplistic here. So probability, by definition, is the likelihood or chance of a given outcome or an event. And in the health sciences and environmental health in particular, we tend to think of things as being good, protective, healthy, nice things, or being risky. And risk, by definition, is a probability, and risk is the probability of an adverse effect or an adverse outcome. It could be the probability of dying, the probability of getting cancer, the probability of getting injured on the job. There are certain things that people may do at work, like working on trenches, being in the hole or in the ground and not having trench support. What's the probability that that wall might collapse on that person? So there are things that we may describe as being risky, which we may not necessarily know the true probability, but we know that the probability of getting hurt is a lot higher than other types of things that might be done on the job relative. But risk by itself, risk by definition is the probability of an adverse outcome. And then if you just happen to have something lucky happen to you, that's the probability of something good happening, presumably at random. So these things can be mathematically or statistically determined if you actually know the denominator. So the numerator is the event, the denominator is the actual total population that you're comparing against. So our numerator, the number of events, the denominator, number of possibilities or number of people. So probabilities can be expressed in mathematical terms. The number of events cannot exceed the number of possibilities. So the number of people who get cancer cannot exceed the total population. So probabilities always are going to be between 0 and 1. They're always going to be fractions that can be expressed between 0 and 1. So say there are 100 people at the university that are there over winter break, and 20 of the students get the flu, and there are only 100 people possible that are staying, in this one particular residence hall during winter break. So the probability or the risk of the flu would be 20 out of 100. That is 0.20. Probabilities can be expressed per centennial or percent. That's by multiplying by 100. So a centennial, that number, centennial, like a bicentennial, centennial refers to 100. So per centennial means per 100. So when we multiply things by 100, we express them as a percent. So 0.20 times 100 gives us 20%, which also means 20 per centennial or 20 per 100. You can also take a probability, and you'll see this done a lot with cancers in the cancer data that are usually expressed per 10,000 or per 100,000. So you can multiply any probability by the number that you want to express it as and get that result. So we could scale this up. Instead of it being 20 cases per 100 as 20%, we can express it per 10,000 and get 20 cases per 100, scale it up, multiply it all by 1,000 and get, or by 10,000 and get 2,000 cases per 10,000 people. It's all still the same probability of 0.20 or 20%. So probabilities are often viewed by us and the sciences when you're doing research. It's kind of like the probability of an event happening plus the probability of it not happening. Those should add up to 100%. So we want to try to capture every scenario. So out of those 20 people who had the flu out of 100, the probability of getting the flu was 20%, 0.20. But what was the probability of not getting the flu? So if the probability of getting it was 0.20, then the probability is the inverse of that. So 1 minus 0.20, or 80%. So 0.80 or 80% is the probability of not getting the flu. Maybe you could consider those folks, what was the probability of being lucky? 80%. So probability of flu plus probability of no flu should equal up to 100%. So you can see some of this show up in health literature. This is a study that was looking at bacterial water quality and viral water quality to predict swimming associated illnesses at a beach. And in this particular study, we've got data on gastrointestinal problems, so like diarrhea, vomiting, that kind of stuff. And these people were followed at the beach, so they were enrolled at the beach on a particular day that they were showing up to go swimming. And then they were called a week later and asked whether or not they had any diarrhea or vomiting or anything like that, along with a bunch of other symptoms. So there were 600 people that were at the study site that were healthy and susceptible to disease at enrollment. So there's the 600. And then 7 days later, out of these 600, 562 of them reported gastrointestinal or no gastrointestinal problems, and 38 or 6.3% had some type of gastrointestinal illness. So what's the probability, or you could also call it the risk, of gastrointestinal illness or GI illness among swimmers that follow up? So we have to know the total population at risk. So how many total swimmers were there at follow-up? So we need to know the number of people who were at the beach who actually had the GI illness. So if we know GI illness divided by the total population at risk, we can get the risk of gastrointestinal illness at follow-up. So there's our formula for risk or probability of GI illness. GI illness over the total sample population. So total GI illness, 38, that's our numerator. Total population, well, it's not just the number who reported no GI problems. It's also these people plus those people. So 38 plus 562, which is our starting 600. So we had 562 with no illness, 38 with GI illness. That represents our total population at risk. The number of people with GI illness, so we got it right there, 38 with GI illness. So 38 divided by the total population, so 38 divided by 600. So the risk of GI illness was 6.33%. Easy enough. So if 6.33% had GI illness at follow-up, just using our general rule that we had before, what's the probability of not having GI illness? So if your risk of GI illness, if you were a swimmer, was 6.33% at follow-up, what would be your risk of GI illness? Or at least, what would be your risk of not having GI illness? So if your risk was 6.33% of having it, what's your probability of not having it? So the probability of not having it would be 1 minus 0.0633, or 100% minus 6.33, so it'll be about 94%. 93.67% is the probability of not having GI illness. So a little bit more onto this. On a standard set of dice, what's the probability of rolling a 6 when using a single die, just a regular die, assuming that it's not loaded or anything? So it's pretty simple. 1 divided by 6, you have a 16.67% chance. Okay, now using our logic here, what's the probability of rolling something other than a 6, like a 1, 2, 3, 4, 5, or 5? So it's the opposite of, if we have 16.67%, this is the opposite of it. So it's 1 minus 0.167, or 83.33%. So 83%, that's our probability of rolling something other than a 6. So why do we care about this probability business? Well, in statistics, we rely a lot on probability. It helps us make a lot of inferences. Particularly, we use a p-value approach in much of the basic biostatistics. The p-value approach is heavily relied upon for determining when there are significant differences between groups or significant effects from different treatments or exposures, or for us to determine whether or not there is no significant effect or significant difference from a treatment or between populations or groups. So we use this p-value approach, or this probability value-based approach, a lot in stats, and I'll get into some examples here shortly. So many decisions or inferences about the data are made using the p-value approach, and most oftenly it's around this number of 0.05, which is where alpha is often set by just kind of a rule of thumb or a general norm. There's not necessarily any reason that I know of other than that's just kind of the rule of thumb. Maybe there is some statistically sound reason for why we choose 95% confidence intervals and an alpha of 0.05 and a p-value of that level of 0.05, but this is kind of the norm. Some epidemiologists like to loosen that and relax it a little bit. Some folks like to strengthen that up and use things like p-values less than 0.01, depending upon how many comparisons and things they may be making. So the p-value approach and alpha. So alpha, that's the Greek letter alpha, that is supposed to be set by the researcher or statistician, often a priori before they do their analysis, as a probability level or a threshold that we may use to reject a null hypothesis and assume that there's some significant effect or true difference that really exists. When we set our alpha at 0.05, that means that we as the researchers are willing to accept a 5% chance of erring in suggesting that an actual difference or an effect exists when in fact it may not exist. So we're willing to accept that 5% chance. So 95 times or more out of 100 will be right in saying that there's a difference or an effect, and then 5% or less of the time we'd be saying something that's not in fact true. Remember, our studies are done on samples, not on the entire population. So we're making inferences based off of our sample sizes and using the software to help us there. So at an alpha level of 0.01, that means that we're willing to accept a 1% probability of erring. So that means that we would believe that 99 times out of 100 that a true effect or difference actually exists when we had a p-value of less than 0.01. So we're going to get more into this here in a second. So I'm going to pause this and we're going to go to reviewing these last couple slides. We're going to take a little bit more time with them because it's complicated stuff. but this is the foundation in which a lot of decision making and stats happens to be done. So stay tuned and watch the next one.